I mean, now let's look at another, because the trigonometric derivatives were actually what we did was just the formulas. Yeah, we didn't do much like challenge things. It was just the formulas, but then we need them to solve different problems, to solve like for instance, even the chain rule, we will need the trigonometric formulas. Okay, that means chain rule. This will be a new rule of finding the derivative for more complex functions. We call like composite of two functions or compound function. I mean, for instance, I can tell you sine square of x. What is the derivative? Or maybe another function, square root of cosine of x. What is the derivative? Yes, or 1 over square root, or that's maybe, oh no, I don't even have to say square root of x cubed plus 1, for instance. What is the derivative? Okay, that's we can combine two functions. We can I can provide composition of two functions, but the idea is how we can find the derivative of these complex functions. We will need additional tool, and the tool is called chain rule. We will have a chain of events, the chain of derivatives. That's me. Let's let me 1 second. Second. Oh, what I'm doing. Okay, let me. Okay, I'm back. I was just looking at the slides. First of all, let's look at the pre-calculus, like algebra, like definition of the composition of two functions. This is the notation, okay? F compound with G of X. And the meaning is F is the outer function and G is the inner function. Okay? That's how we have to understand this. That's when we always see like a outer formula and we will see the inner formula. And domain, in order to figure out the domain, we have to like satisfy both of the functions. Just the theoretical notes. And what I wanted to do, I wanted to give you, for instance, two functions, and I will ask you to get the composition. That means what will be the formula when we have function x squared, function f, and g is sine of x. And now I would like to make the composition f compound with g. Because if we will know, and this is still like algebra, like pre-calc, if we will identify the outer and the inner function, then we will have no problem to get the derivative, because that's the point. Okay, f is the outer function. That means x squared is the outer function. But now, in order to combine f compound with g, we will take the outer function f of x, x squared, and instead of x, we will replace x with g of x. That's when we will do something like this. It was x squared, but we will put instead of x the new formula. That means this is the composition f compound with g, having f x squared and g sine of x. Or actually the proper notation for the trigonometric is this one, but this is also equivalent. Okay, that we can see as sine square of x. The outer function is the square, the power function. The inner function is sine of x. Yeah, really important to identify. Okay, now, oh, I did type this because I usually, okay, now, square root of x and 5x cubed. Please tell me what will be the composition. You can type, I think. F compound with g. Now f is square root of x. But we don't want x. We want a new function in like, yes, under the square root, inside the square root. Yeah? The function, the composition will be, I hope somebody's typing, square root of g of x. Yes, thank you, correct. Square root of 5x cube. Yes, cube. Okay. Now, tangent of x and 1 over x. Yes, it's fine. I figure out that 2 is just a typo. Let's combine and create f of g of x. F of g of x. It means tangent, yes, tangent is the outer function. Instead of x, we will put a new function. Yeah, that's we can see tangent is the outer function, inner function is 1 over x. What about this? If I will ask you the other way, g compound with f, g of f of x, what will be the formula? G is the outer function. We can see what's the formula for g of x, 1 over x. That means now we will have 1 over f of x, 1 over tangent of x. What is 1 over tangent? Yes, thank you, Enoch, and thank you, Sophia. 1 over tangent is cotangent. Oh, funny. We can still, yes, we can. This one we can probably still use the quotient rule, yeah, but I can, we have to even, yeah, it's quite interesting, this one. 1 over tangent, that's mean we will think that 1 over x is the outer function, like, yeah, and tangent is the inner function. Here, for the first, the top line on this, yes, on this part, tangent is the outer function, 1 over x is the inner quantity. Okay, and now, when we see the composition of two functions and we know how to identify outer and inner function, we have to find the derivative. And the derivative, outer, inner, derivative of this function is just the product of, not the product rule. No, just the product of derivative of outer function times derivative of the inner function. Oh, I can actually write this down. Okay, we will have derivative of outer function times derivative of the inner function. We have to identify. However, outer function will still depend on the identical inner function. That means this is sometimes a little bit maybe challenge or confusing, but when we practice, it's nice and clear. And the inner function just depends on x. Right? That means maybe this is, yeah, derivative of the outer function times derivative of the inner. Yeah? But outer function, the input, it's still like the same inner function that it was. Right, but in general, just the product of two functions. Yeah, okay, that means let's just, yeah, that's everything. But let's practice, okay? Let's practice a little bit. Okay, I have, yes, I type this, derivative of f is f prime times g prime, but f depends on g. Or if we like, we can use the Leibniz notation, derivative dy dx, derivative of y with respect to x, is derivative of y with respect to u will be like the inner function, and then times derivative of the inner function, u with respect to x. Okay? Okay. whichever is easier form. But let's try. Okay, I just said this. It's the same thing, outer, inner. Okay, that's it. For instance, let's start with this. Yeah, if you can get the derivative without any problem, that's good. That's mean that you understand the chain rule. Okay, find the derivative of this function, square root of x squared plus 1. That's what we can do. I know that for most of the students, it is helpful maybe to name the inner quantity as as a new variable. That's what is the inner quantity? What is the inner quantity? If we have the function square root of x squared plus 1, what's the inner function? Yes, it is x squared plus 1. That means I can say, yes, I can say that x squared plus 1 is u. And then we have just square root of u. Okay, we have just square root of u. Now we can differentiate square root of u. We will still differentiate u, but let's at least start this. Okay, what's the derivative of square root of u? When we have, like, for instance, square root of x, what's the derivative? 1 over 2 square root of x. Yes, everybody's okay, because square root of x is x to the power of 1/2, and we can use the power rule. X to the power of 1/2, derivative is 1/2, x to the power of negative half, because we're subtracting 1. And when I rewrite without the negative exponent, it will be 1 over 2 root x. Okay, that means this is the derivative of square root of x. Square root of x is quite good friend of ours. We have to, yes, like, know. Okay, that means derivative of square root of u is 1 over 2 square root of u. And this is the outer function times derivative of the inner function times derivative of that u. Okay, remember, outer times inner. And now I can remove that u and I can actually put x squared. That means instead of u, I will put back, I mean the x variable. I will put back the original formula because u was defined as x squared plus 1. That's the inner function. And times derivative of this x squared plus 1. What's the derivative of x squared plus 1? Derivative of x squared plus 1 is 2x. Okay, we can cancel out 2 and that's it. I know you will probably skip the u notation later, but let's do maybe a couple of first examples doing this. Okay, let's look at example number 2. Oh, this one is a little bit different. It is sine of x squared. That means what is the inner quantity? This one is not, we're not squaring the sine. It's just sine function of x squared. That means what's the inner function? What's the inner quantity? X squared. Yes, inner quantity is x squared. Okay, that's we have sine of u. We know that behind u we have a new function. I mean the inner function. Okay, that's what's the derivative of sine of u? We just learned, yes, what's the derivative of sine of x, but now we have sine of u.
Cos of u.
Oh, Kriti, I don't know if I heard you. Did you say cosine of u?
Yeah.
Okay, that means derivative of sine of u is cosine of u, but now we follow the chain rule. Yes, because that was the chain rule, the sine of u times derivative of u. So we can see from now on, we always have to think that u may be like another function. If this will be sine of x, yes, sine of x, derivative with respect to x, of course, we will say cosine of x. But if I am not sure, I can still think times derivative of x, but derivative of x is 1. Yeah, that means I can even use the chain rule for basic variable, but this is that chain times derivative of the inner quantity times derivative of the inner quantity. That means cosine of u times u prime. Yeah? And u is x squared. That means derivative of, that's what I was saying, that maybe you may skip the u. Derivative of sine of x squared. It is cosine of the same thing, x squared, times derivative of x squared. Yeah? And this is that chain. That's the chain. Derivative of x squared is 2x. That means this is the final answer. Okay, 2x times cosine of x squared. We may notice inner functions stayed the same. Okay. I don't look at this. We don't need this for now. Now we have this function, sine square of x. Okay, that means now we actually see a sine function squared. That's equivalent notation, maybe even a little bit easier. It means now the inner function is sine of x. The inner function, the u, will be sine of x. Okay? And what we have u squared. Please tell me what's the derivative of u squared? What's the derivative of u squared? The same like x squared, but we will add the chain rule. It's 2u. But we also know that u is the inner function. That means we will say 2u times u prime. Follow the chain rule. And that means this is that chain. I can even chain rule. 2u times u prime. If this will be just x squared, derivative of x squared will be 2x. That's it. But if this is 2u, or I mean u squared or w squared or different variables squared, yes, we don't know. That means it's always safe to say derivative of u squared is 2u times u prime. If u prime is 1, that's fine. But if u prime is different, then we will have correct answer. Now, let's get back. U is sine of x. That means 2 times sine of x times derivative of sine. And derivative of sine is cosine. And I just realized that is the double angle formula, but we don't, that's not the point at this moment. This is the answer. And yes, you may tell me the answer right away. Yeah? Like derivative of sine square of x. It's squared. That means you will say 2 times sine of x times derivative of sine. But if you like the u notation, it's perfect at the beginning, of course. I mean, anytime you can use the u. Okay, let's keep working. E to the power of x cubed plus sine of x. Okay. What's the inner function? Oh, okay, I type it. The inner is the entire exponent. That's we just have e to the u. What is the derivative of e to the u? Who can type? Maybe you can type with the chain rule. E to the u. Oh, what's the derivative of e to the x? Derivative with respect to x is just the same function. Yes, exponential. E to the x is just e to the x. Then e to the u is just e to the u. But we will multiply by u prime. Derivative of e to the u is e to the u times derivative of that exponent u, which is u prime. Now I can replace u is x cubed plus sine of x times derivative of x cubed plus sine of x, 3x squared plus cosine of x, and we can leave it like this. Yes, that's we can see the chain rule. Derivative of the outer function, which depends of the inner, and times derivative of the inner. And that's what I was like. That's how the formula, we just follow the formula. Okay. Now I also typed all of the trigonometric formulas, but adding the chain rule. So in derivative of sine of u will be cosine of u times u prime. Cosine of u is negative sine of u times u prime, and so on. Secant square of u times u prime. negative cosecant square of u times u prime, yeah, times derivative of the inner function, because we don't know what is u, could be a new function. Secant is secant times tangent, secant of u, tangent of u times u prime, and negative cosecant cotangent u times u prime. Okay, you have to remember. Okay, what else I have? Something interesting. Yeah, this is just the formula. When we have u to the power of n, we just did this. We will follow the power rule. Yes, n u to the power of n minus 1 times u prime, because actually this notation is u prime. U prime is just shorter to say du dx. Or if I name u g of x or other function, yeah, that's the same thing. That's actually the same thing. Okay, I was just trying to type everything that it will be helpful. And okay, I have this example. Derivative of x cubed minus 1 to the power of 10. And I think I did it without u. I mean, without the u verbal. Let's see what I have. This is inner quantity. That means this inner quantity is taken to the power of 10. Derivative of something taken to the power of 10 is 10 times the quantity to the power of 9. This is 9. Times derivative of this quantity. Yeah? You may think it's u to the power of 10. Derivative of u to the power of 10 is u to the power of 9 times u prime. That's basically, we can see that's basically this, 10 times u to the power of 9 times u prime. Derivative of x cubed minus 1 is 3x squared. And I can maybe multiply these two, but it's fine. Yeah, I hope that's the, and then I have plenty of examples in this presentation you can go through. Let's maybe solve a couple of more, and then you can practice and practice. I have this one, but I can leave it for you. Okay, that quantity, we can see 1 over cube root of this expression. That means this expression is taken to the power of negative 1/3. I just rewrite this as a power function. I mean power form. And then we can use the power form for outer function and times the derivative of the inner. You can check this later. I have this one. Oh, we may also have more than one inner function. Yeah, then we will follow, like we will multiply by the derivatives of the most inner function. And let's look at this one. Square root of secant of x cubed. That we have to differentiate square root times derivative of secant times derivative of x cubed. And we will follow the chain rule. So let's see. Derivative of square root is, yes, we remember, square root of x is 1 over 2 square root of x. That means derivative of square root is 1 over 2 square root, identical quantity inside, we can see, times derivative of this inside function. Yeah, that's the chain rule. Derivative of secant, we just learned, yes, derivative of secant, but secant of x is secant times tangent. But now our x will be x cubed. If this is x cubed, this will be x cubed. And since this is inner function, we will multiply by derivative of that x cubed, 3x squared. Let's do it. I copy this. Derivative of secant is secant times tangent of the same inner function, we can see, times derivative of this inner function. That means we did kind of like, we did apply chain rule twice. Okay. Okay, and that's it. No other simplification. I can put everything on the top. Okay. Oh, too fast. Okay, sine of cosine of tangent, but you can try this, you can try this. Oh, I have some of the solutions because it's so many things. I just want to, you can try this one. Too many things. They are such a nice questions. I just want to do. You can try. Okay, let's maybe do this one. Okay, because everything is like a compound function and the chain rule. But let's do maybe a little bit of like application. Okay, spherical balloon has a radius r that is increasing at the rate 3 centimeters per second. Determine at what rate, derivative, yes, dv dt, the rate of change of the volume with respect to time. At what rate the volume V of the balloon is increasing at the moment that R is 10. And that's what we notice. We have a spherical balloon. Okay, we have a sphere. And the radius is increasing. That means radius is a function of time. Okay? It's inner function. And volume is respectively the function of radius, but radius is the function of time. That means volume is also a function of time. That means we will need, first of all, the formula for the volume. Somebody remember? What's the formula for the volume of the sphere? This one. Oh, cube. Of course, cube. 4/3 pi r cubed. And that's the formula. And we have to find out the derivative. Okay? That means normally volume depends on r. And this is the formula, let me just say. And what will be the derivative? This is still old stuff. What's the derivative of 4/3 pi r cubed? R is a variable. Yeah? This is R. Let's say the volume depends on R. We will copy constant, correct? And just differentiate R cubed, 3R squared. 4 pi R squared. Oh, yes, okay, yes, thank you. Because we will just cancel out, that's actually good. Derivative, it's basically 4 pi R squared. Perfect, that's good. But now we have to be a little bit careful because we're looking, yes, I can even say derivative of V with respect to R. Derivative of V with respect to R. Now we have the same formula. What I can do? Volume depends on time. It's still the same formula because you may notice here we didn't use the chain rule because we just have independent variable r cubed, derivative of r cubed is 3r squared. That's it. But this one, yes, this one is r cubed, but r depends on time. That means it's an inner function. Okay, yes, I can keep this way. That's me. Now, what is the derivative of the volume dv dt? Derivative with respect to time. Okay, that's we will follow, yes, copy this, that's constant for 4/3 pi. Now, r cubed. What's the derivative of r cubed? And maybe I can even remove this for a second, but we still have to, yes, remember, I can put it this, r depends on t. That's mean derivative of r cubed, the same thing, 3r squared, but we know that behind r, we have an inner function times r prime, which is dr dt. Yeah, it's more proper notation, but we can see this is the difference. Yeah? Derivative of r cubed, 3r squared, but derivative of r cubed, if r is a function which depends on the other variable of time, will be 3r squared times r prime. Or if we prefer, 4/3 pi 3r squared dr dt, if we like this, this way. Okay? That means dr prime. R prime is the rate of change, the derivative of r with respect to time. Okay, so now let's see what we have. Actually, we can still cancel out. We will have 4 pi r squared and dr dt. And now they asking us determine the rate of change, dv dt. This is actually the rate of change, dv dt, of the volume of the balloon. Like the rate of change of the volume, like how the volume is changing, increasing at the moment when the radius is 10. That's when we can just substitute 10, r squared will be 10 squared, but we also know the rate of change because they providing us. The spherical balloon has a radius r and it's increasing at the rate. Yeah, that's mean rate, how can I say, r prime, or the rate of change of r with respect to time. It's that quantity, 3 centimeters per second. Okay, that's when I can substitute 3. Who can help me this? 1200 pi. And it will be centimeters per second, the rate of change of the volume. We can still multiply by pi, but it's fine. Okay, but we can see the main message will be this. Yeah, please do not miss the chain rule if the variable seems to be like another function which depends on the other variable. Okay, this one is fine. This one is just but we need this because everything depends on time. Okay, maybe really quick one more question. You can do this one. It's the same, almost the same. Let's do this one as a last one, okay? The power P in the circuit is defined. That's me now. Let's see. We have the formula. The power is defined as a R times I squared. I, not R. I. Okay. Where R is the resistance and I is a current. Find derivative of P with respect to time. That's when we have to differentiate P with respect to time. At the moment when time T is 1/3, fine. At T, yes, at T being 1/3, and the resistance is 1000 ohms. Ohms, I think that's how we call this. Okay, that's we have time. Yes, time is 1/3. Resistance is given 1000 ohms, and I is a function, yes, that changes with respect to time, but even has its own formula, 4 pi t. That's mean behind I we have a function. Okay. That's mean normally, if this will be derivative of the power, let's say with respect to I. With respect to I. Yeah, that's mean I can also say P prime, but prime it's not giving us more detail. Like this notation is giving us lots of details about the variable because it's sitting in the denominator. Okay, that's mean if I have to differentiate this formula just with respect to I am assuming that R is a constant and derivative of I squared is 2I. That's it. But now I know that I has a function. Then I will multiply by I prime. Okay, that's mean now we will copy derivative of R I squared. Copy R because R is constant. I squared. Yes, I is not constant, is changing. Derivative of I squared is 2I. Why I am writing R? 2I times I prime. But let me be a little bit more details. I prime means derivative of I with respect to time, because we differentiating with respect to time. And I can also say P prime derivative, but again, prime is not detailed like notation. And that's we can see this is the chain rule. I squared, derivative of I squared is 2I times I prime. We know what I prime is derivative of I with respect to the variable that is provided, time. Okay? That means this is the proper, please do not forget what I did. Derivative of I squared is here. Yeah, times I prime. All this, the same thing I just. And now let's just substitute. The resistance was 1000, 2 times. Hang on, we have the formula. We have the formula, we don't have just value. Okay, R, we didn't finish. 2, what is actually I? Please tell me, what is I? How I is defined? How I is defined? Can you tell me? Because we don't, not like the previous one. I is defined as a sine, yes, thank you, Elliot, for typing, 4 pi t, okay, and now, this is the main point. What is I prime? What is the derivative of I? With respect to t. What's the derivative of? Can I squeeze here? What's the derivative of sine function? We learned today. Cosine, yes, of the same inner function, that's mean derivative of sine, 4 pi t, is cosine of 4 pi t times derivative of the inner quantity. Derivative of 4 pi t, t is the variable, is 4 pi. Yes, like derivative of 2x is 2. Derivative of pi x is pi. Derivative of 4 pi x is 4 pi. Our x is t, okay? That means times 4 pi. That means derivative is cosine of the same inner function, 4 pi t, times 4 pi. Derivative of the most inner function. That's the finished problem. Okay, now we can substitute values. That means derivative of the power with respect to time is 1000 times 2. Time is 1/3. That means time will be 4 pi over 3 times cosine of 4 pi over 3 and times 4 pi. 8,000 pi. And we need this. What is sine of 4 pi over 3? And what is cosine of 4 pi over 3? Really quick, and we will finish the session. That's 60 degrees, but it's 240, third quadrant. This will be square root of 3 over 2, but negative. And this will be 1/2, but negative. Am I right? I hope. 2 times 2, 4. That means this will be 2000. I can cancel out 2000 pi, negative and negative positive, times square root of 3. I can maybe write 2000 square root of 3 pi. That's 3. Okay, this is the rate of change of the power, yes, with respect to time. With respect to time. I can skip the units, but it's like a power, whatever the units are for the power, over the time units. I don't know, seconds, time. Yeah, we don't have it. Okay. But yes, this is important. That's I and that's I prime. Okay, really nice question. And I hope we understand the chain rule. Please go through the practice problems, the easy problems that I skipped, and also this couple of applications. And I'm sure you will Yes, have no problem in this week assignments. This is, of course, I did cover half of the week. You still have a second half tomorrow with Isaac. Okay, enjoy the new concert. Do not waste any minute, okay? Work every day. Thank you and see you next week.
Have a good